pi bond electrons shifting from double bonds to single bond. In that process, there is energy also released. That energy we call the resonance energy. So in this session, I will explain the resonance energy. So what is the meaning of resonance energy? So there is the definition of resonance energy. Resonance energy, that is equal to the energy difference between more stable resonating structure, and hybrid structure. So that is called the resonance energy. So more stable resonating structure and hybrid structure, we know that. So the energy difference between the more stable resonating structure and hybrid structure, we say that resonance energy for the definition purpose. For the calculation purpose, resonance energy is, that is means theoretical heat of hydrogenation minus practical heat of hydrogenation. Theoretical heat of hydrogenation subtract practical heat of hydrogenation. What is the theoretical heat of hydrogenation? It means to multiply the number of pi bonds with the 28.6. There is number of pi bonds multiplied by 28.6 kilocalorie per mole. We know that already. 28.6 kilocalorie per mole. What is that? Right. If there is one pi bond is hydrogenated, their liberation of energy 28.6 kilocalorie per mole. So resonance energy automatically, we know that, depend on the resonance energy depend on heat of hydrogenation. Heat of hydrogenation पे depend हो रहा है. Okay, right. So come to the one question. I will explain the what is the theoretical heat of hydrogenation, what is the practical heat of hydrogenation. Theoretical heat of hydrogenation means you have to calculate the multiply the number of pi bonds with the 28.6, be getting the theoretical value. So what is the practical value? The examiner will be giving the question paper. That is the practical value. So experimental value, that will be there in the paper. So come to the one question. So here is the one pi bond for this heat of hydrogenation, delta H, that is equal to 28.6 kilocalorie per mole. We know that this is the exothermic, that's why I mentioned the minus exothermic. Okay, at the same time I give the this one structure. This is the 1,3 butadiene. For this delta H, how much? What about the delta H? So there is the 2 pi bonds will be there. So then we have to calculate the 28.6 into 2. So 28.6 multiplied 2, 2 6 are 12, 2 is the 16, 17, and 2 is the 4 and 5, 57.2. That value is the 57.2. That is theoretical. It means number of pi bonds multiplied with the 28.6. What is the practical value? Practical value will be there in the paper. Practical value. So delta H, experimental value by the hydrogenation of this 1,3 butadiene, by the experimentally, the delta H, that is equal to 54.2 kilocalorie per mole. So this is also exothermic, this is also exothermic, but what is the resonance energy? Theoretical heat of hydrogenation minus practical heat of hydrogenation. There is a negative is indication exothermic. It is not a negative value. Okay. So theoretical heat of hydrogenation minus practical heat of hydrogenation. When you substitute the values, we are getting the resonance energy. So resonance energy, that is equal to theoretical value 57.2, and what about practical value 54.2. So I think 54 minus 57, it means 3. 2 to cancel, okay, 3 kilocalorie per mole. For this resonance energy, how much we getting there? 3 kilocalorie per mole. So when the pi electrons are moving like that, their energy also release. That energy is called the, okay, resonance energy. So resonance energy to depend on the heat of hydrogenation. So theoretical matlab there is number of pi bonds multiplied with the 28.6. Okay. Then come to the benzene. So what is the theoretical value? So there is 3 pi bonds are there. 28.6 into 3. So 3 6 the 18. 1, 24 and 25. 3 12, 6, 7, 8, 85. So theoretical value delta H, that is equal to 85.8 kilocalorie per mole for the benzene heat of hydrogenation. So delta H equal to delta H, that is equal to 85.8. So there is 3 pi bonds are multiplied with the 28.6 kilocalorie per mole. So we know that exothermics, so there is to mention the minus is an indication exothermic, it is not a negative value. Okay. So what about practical value? Practical value there is 49.2. So it will be given in the paper. Practical value delta H, that is equal to 49.2. So when these two values put in the theoretical value minus practical value, then we have getting the resonance energy. So resonance energy, that is equal to theoretical heat of hydrogenation minus practical heat of hydrogenation. What about theoretical heat of hydrogenation value? Right, very good. 85.8 minus 49.2. When it is to subtract, so we are getting the 36.6 kilocalorie per mole. So finally the resonance energy of the benzene 36.6 kilocalorie per mole. So this is the value of resonance energy for the benzene. Okay, understood? So there is nothing, just you have to listen here. Resonance energy means in the process there is the pi electrons or lone pair electrons are moving from single bond side in the conjugation side. So when they are rotating like that, double to single, single to double, double to single, for in the process there is a energies release. That energies we call the resonance energy. So resonance energy to depend on the heat of hydrogenation. So that is the theoretical value minus practical value. Theoretical means number of pi bonds multiplied with the 28.6. And resonance energy also depend on the number of resonating structures and depend on the equivalent resonating structures, depend on the overlapping of lone pair of electrons, depending on the aromatic, non-aromatic, anti-aromatic, and depending on the electronegativity, okay, depending on the external resonance. Okay, so the remaining topics I will explain the next session. So note down the first this. Okay, right. I will explain next slide. Right. Now in this session I will explain the resonance energy and remaining points. Okay. So resonance energy directly proportional to number of resonating structures. Number of resonating structures. It means resonating structures increases as well as resonance energy also increases. Okay. So I will give them an example for this point. Resonance energy depend on the number of resonating structure. Resonance energy increase when if number of resonating structure increases. So come to this question. There will be 2 pi bonds in this question, and here is a 3 pi bonds. So obviously the resonating structures is more in this question. Okay. So if there is number of pi bonds increases, automatically resonating structures also increases. Okay. So finally the resonating structure increases for this question. So automatically resonance energy also increases now. Right? And second question, I will give this one. Okay? And the second one. We know that already this is the benzene. This is the diene. So resonance energy for the benzene 36.6 kilocalorie per mole. For the double bond 3 kilocalorie per mole. Already we calculated in the previous class. There is 2 pi bonds are there. To multiply with the 28.6, we getting the how much work value? Okay, 57.2. Then minus practical value kitna? Right, 54. So then we getting the 3 kilocalorie per mole. So resonance energy here is the excess, because there is the pi bonds increases, automatically resonance energy is also increases. Understood? Right. So come to the second question. Resonance energy directly proportional to number of equivalent resonating structures. We know that equivalent resonating structures, there is the energy is the same. Okay, there is the energy is the same in all the resonating structures. That is called the equivalent resonating structures. For example, either there is SO3 minus, and here is the CH3C double bond O minus, and here is the benzene, there is a minus. We know that these two are to give the equivalent resonating structure. So each of the resonating structure consists the same energy. That is called the equivalent resonating structures. So what we are getting the resonating structure by the overlapping of negative electrons. So that each of structure is getting the same energy. That's why we call the equivalent resonating structures. But in this process, there is a negative electrons are overlapping towards to the benzene side, but there is different resonating structures are will be formed, and they consist different energy also. But here is the we getting the same energy due to same structure will be formed. So now here is the oxygen getting the minus, then after the overlapping this negative electron, this oxygen getting the negative, but there is the same structure now. First this oxygen getting negative, then after second one this is getting the negative, and in second time this oxygen getting the double bond. There will be the structure is the same now. Okay, that is the equivalent resonating structures. That equivalent resonating structure consists the same energy. There is no difference in the energy difference. Okay, but compared to the first option and second option, here is we getting the 3 equivalent resonating structures. So sulfur, there is oxygen minus, there is double bond O, there is double bond O. So once it negative electrons come this side, we getting like one structure, and maybe these negative electrons come this side, we getting this side. So finally there is 3 oxygens are present. So there is 3 resonating structures formed. That 3 resonating structures consist the same energy also. Okay. So now in this time, this oxygen getting negative, then second time this oxygen getting negative, and the third time this oxygen getting the negative. Finally each of oxygen once they getting the negative charge and they getting the double bond, but structurally that is same. That is called the equivalent resonating structures. Okay, come to this question. So maybe electrons are overlapping like that. Now this structure and this structure is both are similar. Okay, but these two are called the equivalent resonating structure. So structurally is the same, atomical energy also same. So what is the resonance energy and depend on the number of equivalent resonating structures. So the component which is getting the number of equivalent resonating structure, that is consists the resonance energy is excess. So finally the first one getting the excess of resonating structure, and the same resonance energy also is increase. And here is the resonating structures will be formed, but these are the normal resonating structures. There is the structures are different, energy also different, but here is the structures are same, energy also same. But compared to the first and second, the first one is give the number of resonating structure that all be equal, and there is excess resonating structures. Okay, so finally equivalent resonating structure increase हुआ तो resonance energy भी increase होता है. That is understood? Okay. And come to the third point. Resonance energy directly proportional to, it means resonance energy that is equal to extended resonance greater than cross resonance. So extended resonance consists the resonance energies more than compared to the cross resonance. So I will give them an example. For this question, here is the positive charge is there, here is a double bond, here is a double bond. Okay, so there is a conjugation is present, double single positive, conjugation is there. So here is the pi electrons are conjugated, and overlapping is continuous is there. And this second question, there is a positive, here is the pi bonds are same, here is also pi bonds 2 there, and here is also pi bonds are 2 there, but resonance energy is not equal. Don't say about that. There is consist same is resonance energy. That is wrong. Here in this example, there is a pi bond electrons are conjugation in there, but that conjugation is continuous. Double single positive, continuous conjugation. But here double single positive, from this side double single positive, there will be possible from this side way of conjugation, and here is also that side also conjugation is possible. Both sides conjugation, that is called the cross resonance. This is cross resonance. This is continuous resonance, continuous, extended. So there is a pi bonds are same. If there is a pi bonds are same, extended resonance consists the resonance energy is excess than the cross. This one is the cross resonance. Understood? So first one, number of resonating structure increases, automatically there will be resonance energy also increases, equivalent resonating structure increases, automatically resonance energy increases, extended resonance increases, resonance energy increases. Extended resonance is more priority than the cross resonance. Okay, right. Next, come to the next topic. Resonance energy directly proportional to, or resonance energy that is equal to aromatic, then non-aromatic, then anti-aromatic. Anti-aromatic. The given component may be aromatic. Given components may be aromatic. They consist the resonance energies excess. For example, I will give one example. This is the benzene. Here is the double bond is there, and here also double bonds also there, but like this. We know already aromatic. What is aromatic? Which can cyclic and planar, okay, complete conjugation, which can follow the Haeckel's rule, 4n plus 2. If follow the 4n, that is anti-aromatic. So finally this is aromatic. We know benzene is aromatic. There is no complete conjugation in that 4 rules. If any one rule is failed, that is non-aromatic. So there is no conjugation completely. This is non-aromatic. Here is anti-aromatic due to there is 4 pi electrons. 4 pi electrons. Here is a 6 pi electrons. Finally, aromatic is excess resonance energy. Aromatic consists the resonance energy is excess then compared to the non-aromatic and anti-aromatic. Understood? And give another example also. So for this example, there is a positive, and here is a double bond, here is a double bond, and here is negative. This is the 2 pi electrons. We know already this is aromatic. There is no conjugation. This is non-aromatic. There is 4 pi electrons, anti-aromatic. The resonance energy will be getting the aromatic is excess, then non-aromatic, then anti-aromatic. Understood? So how many points are over? There is 4 points. Number of the resonating structure increases, resonance increases, equivalent resonating structure increases, resonance energy increases, extend resonance is more priority than the cross resonance, and aromatic is more priority than the non-aromatic and anti-aromatic. Okay, understood? Right. Next one, resonance energy directly proportional to overlapping of lone pair of electrons. Fifth one, there is a fifth one, resonance energy that is equal to overlapping of lone pair of electrons. Overlapping of lone pair of electrons. Okay, so there is a fluorine. They consist the lone pair of electrons. And here is the chlorine. Here also presents lone pair of electron, and here is the bromine. We know that carbon orbital is 2p and fluorine of lone pair of electrons 2p. The energy is same, so overlapping easily possible. Double single lone pair conjugation is there, and this chlorine of lone pair of electrons there in the 3p, and for that bromine consists in the 4p orbital. The easily overlapping in the fluorine due to there is the lone pair of electrons present in the 2p orbital. At the same time, carbon orbital is a 2p, 1s2, 2s2, 2p4, p orbital is present, 2 series. There is no d orbital. 2p energy is same, so the momentum of electron easily possible compared to the fluorine and bromine. So the resonance energy automatically fluorine, then chlorine, then bromine. I will give the another question. So maybe in the question paper which has highest resonance energy, in the question paper there, which has highest resonance energy. So resonance energy is directly proportional to overlapping of lone pair of electrons. So that is easily possible in the fluorine, the first and then second, then third. Understood? Right. Next, topic number 6. In the sixth topic, resonance energy inversely proportional to electronegativity. Resonance energy बढ़ना है, electronegativity कम होना है. Okay. Sixth, resonance energy inversely proportional to electronegativity. Exception: halogens, fluorine, chlorine, bromine, iodine. These are the exceptions. Due to in the halogens there is overlapping of lone pair of electrons depend. So I will give them an example. There is a double bond and there nitrogen, and here is also double bond and oxygen. So nitrogen also consists lone pair of electrons and oxygen also consists lone pair of electrons. But which is easily to donate of lone pair of electrons? Which lone pair of electrons are easily delocalized? So we know that electronegativity, that is equal to nitrogen greater than oxygen. Nitrogen is greater than oxygen. So obviously the nitrogen will give easily lone pair of electron to other due to its electronegativity is less. We know that already. Electronegativity means electrons attracting tendency. Now the nitrogen is getting the lower electronegativity, that's why it can easily to donate the lone pair of electrons. Understood? And come to the oxygen. This will be also give the lone pair of electrons, but compared to the nitrogen, not easily. I will give the next question. So the resonance energy which is getting is more for the nitrogen. Okay. For example, if there is NH2 is there present on the benzene ring, and maybe is there oxygen is there. So which have highest resonance energy means anything. And maybe is there OH and maybe is there SH. We know oxygen is greater than sulfur electronegativity. So finally, resonance energy is Theo, then alcohol. Understood? Right. Next one. Next one, seventh one. Resonance energy directly proportional to number of benzenoids. Resonance energy directly proportional to number of benzenoids. This is the seventh rule. If there is benzene rings increases, automatically resonance energy also increases. So I mentioned the benzene, and the second one naphthalene. This is the naphthalene. The next one anthracene. The next one phenanthracene. Benzene, naphthalene. This is anthracene. This is phenanthracene. So benzene rings increases compared to the first and second. There is 2 and there is 3, but you see in the anthracene and phenanthracene there are same. So there is resonating structures for the benzene 2, for the naphthalene 3, number of resonating structures. Anthracene will give 4. phenanthracene will give 5. But anthracene, phenanthracene having same number of benzenes, but there is in the difference in the resonating structures. The anthracene will give the 4. Yeah? You remember this? So keep it in mind. Resonance energy, there is benzene will be give excess, or phenanthracene will be give excess. Very good. Phenanthracene will be give excess. 1, 2, 3 and 4. So the excess of resonance energy which will be give phenanthracene, then anthracene, then naphthalene, then benzene. So 1, 2, 3, there is benzene ring increases. So obviously third one is give the excess of resonance energy, but fourth one they will be give excess of energy then compared to the anthracene, due to phenanthracene will give the 5 resonating structures. In the first topic, resonance energy directly proportional to number of resonating structure, the first rule. That can be too applicable here, but there is the same benzene rings. Here is also 3, there is also 3, but here is the resonating structures are excess. That's why anthracene give the resonance energies excess then compared to the, sorry, phenanthracene give the excess then compared to the anthracene, then naphthalene, then benzene. Understood? So note down. I will give some more example in the next session. Okay.